Water runs into a tank that is in the shape of an inverted right circular cone at the rate of 9 cubic feet per minute. The tank has a height of 10 feet and a base diameter of 10 feet. How fast is the water level rising when the water is 6 feet deep? Thinking about my process for solving a related raise problem, the first thing I want to do is draw a picture. So my tank is in the shape of an inverted right circular cone. So here's my cone. And what I can imagine is a right circular cone, so I know that the height is perpendicular to its radius, right? And I'm told the height is 10 feet, and I'm told the base diameter is 10 feet, so instead I'm going to think about the radius being 5 feet. All right, because all the way across would be the diameter, and there's my nice little 5 feet. And I'm imagining there's water in my tank, and I know water is being added to the tank, and I could just imagine it being filled in because I'm given that it's being filled in at a rate of 9 cubic feet per minute. So right away, I want to think of that as dV dt. That's the rate of change of volume. And I know that for a couple reasons. Number one, if I was filling a tank, the most reasonable way to keep track of how much water I'm putting in would be in terms of volume, but also it's cubic feet per minute, right? Cubic feet is a measure of volume per minute. There's my rate of change of volume. So I'm given information about dV dt, and I'm asked to find how fast the water level is rising when the water is 6 feet deep. How high the water level is rising, I think I'm being asked to find a rate of change of height. So I'm going to introduce some variables. I'm going to call the radius of the water R, and I'm going to call the height of the water H. Not super creative. The volume of the water I've already decided to call V. Well, one nice thing, because my tank is an inverted right circular cone, the shape the water makes in the bottom is also an inverted right circular cone. So I'll write down an equation for the volume of the water. The volume in the water would be 1/3 pi R squared H. That's the formula for the volume of a right circular cone. But I want to point out when I write that down, I'm talking about this R and this H. I'm talking about just the water, not the tank itself. The tank would have a bigger radius, right? My water's being filled up slowly. And I'm asked about one moment in time where the height of the water is 6 feet deep. So when I talk about the volume in this formula, I'm only talking about the volume of the water, which is changing with respect to time, because I'm putting more water in. If I think about it, the height's changing and the radius would also be changing as the water fills up in this inverted right circular cone. All right, so I'm going to move my diagram and my formula to the next board. So I have a diagram here of my tank, which itself has a radius of 5 feet and a height of 10 feet. Inside my tank, I have a volume of water. And that volume of water is changing because I'm filling the tank up. And I've elected to call the radius of just the water R and the height of just the water H, giving rise to this formula. The volume of the water is 1/3 pi R squared H. I'm given dV dt, which is 9 cubic feet per minute. And I'm looking for the rate of change of the height. I'm asked how fast is the water increasing? Well, right now I could go on and differentiate both sides of this implicitly. But if I think about it, this side would be easy, and this side I'd have to use the product rule, because R is a function on time and so is H. As time moves on, the height increases and so is the radius. So I'd have to use the product rule. And I'm only asked about dH dt, I'm not asked about dr dt, and I'm only given information about dV dt. To use the product rule here, I would end up with both a dH dt and a dr dt. And I don't want that. I want to see if I can use something in this diagram to get this down to only involving the height. And what I see in this diagram are actually two similar triangles. If I look down the middle of the cone, I see a big green right triangle. And that big green right triangle has one side of length 5 and one side of length 10. Inside the water, I have a smaller right triangle with a side length of R and another one of H. I know they're similar triangles because they share all three angles. They share the right angle. This angle is literally in both triangles, and if a triangle shares two angles, it automatically has to share the third. And what I remember about similar triangles is that corresponding sides have to be in the same proportion. So r over 5 has to be the same thing as h over 10, which means r is equal to 1/2 h. At every single moment in time, r is always 1/2 h. So I can update my formula so that it only involves a volume and a height. All right, so I plug 1/2 h in here. I have to square this, so I get 1/4 h squared, but times that h gives me my h cubed. And now my final formula here, 1/3 times 1/4 would be 1/12. So I end up with pi 12ths h cubed. And now I'm down to the two variables that I either have information about or that I want to know. So now I will take a derivative. dv dt is equal to, and the power rule would say 3 pi over 12, and I'll reduce that in a minute, h squared times dh dt. All right, going back to my original problem. I know dv dt, and I'm looking for dh dt in the moment the water is 6 feet deep. So I'm ready to evaluate. 9 cubic feet per minute is equal to, and that's a pi 4ths, times 6 squared times dh dt. So I need to solve this equation for dh dt. So 9 is equal to, and I have pi over 4 times 6 squared, which is 36, times dh dt. That is 9 equals 9 pi dh dt. Divide both sides by 9 pi, and I get that dh dt is 1 over pi feet per minute, a rate of change of a height in feet with respect to time, which is being measured in minutes. If I wanted a decimal approximation, 1 over pi is about 0.32 feet per minute. At the moment, when the height of the water is 6 feet, the height is increasing at a rate of about 0.32 feet per minute.